couple things to look at today. First thing I want to go over is what happens when you have forces that act that counteract the normal force. And you kind of have to pay attention to this. The classic problem is you've got a sled sitting on a flat surface, okay, and somebody's pulling the sled this way with a force of, say, 60 newtons. Say the sled has a mass of 25 kilograms. And let's say that this angle right here is 25 degrees. Okay? And the question will be like, if the velocity is constant, okay, which means the acceleration is 0, what's the coefficient of friction? Okay? And assume this thing is sliding. So find the coefficient of kinetic friction between the block and the sled and the ground if these are the forces that act. Okay? Well, just like everything else, you have to get your coordinate system established. So here's x and y. I'm picking them parallel and perpendicular to the ground. And so then label your forces. Of course, gravity pulls down. The normal force pushes perpendicular to the surface. This is the applied force in this rope. Okay? And it's going to be moving this way. So the frictional force is right here. Okay. And so then if we pick our directions, net force in x, okay, you have to be careful, net force in x is equal to the x component of tension. Just like we have components of weight on an incline, this string is pulling both up and right, so we got to look at the right component. So this would be Ft in x, and this would be Ft in y. Okay, so I've got Ft in x minus the kinetic friction, Fk, equals, according to Newton's second law, ma. And since the acceleration is 0, this is 0, so I can say that the tension in the x direction is equal to the frictional force, Fk. Okay. I'm stuck there, though. I can find Ft. Okay, I guess I can. I'm not stuck. Ftx equals 60 times the cosine of 25, right? And that's because we're looking at a right triangle. We know this side is 60 newtons. We know this angle is 25 degrees. We want this side right here. This is the x side. And so cosine 25 is adjacent over hypotenuse. And so multiplying by 60 gets me x. So I got ftx, 60 cosine 25. And you can have the kinetic frictional force. Okay, but I want the coefficient of kinetic friction. Okay. And remember, the kinetic frictional force is equal to, that's an Fk, the coefficient of kinetic friction times the normal force. So now I need the normal force, okay, which looks like it's right there. But you have to be very, 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 very careful because it's not. Okay? The net force in y needs to be 0 because it's not accelerating up or down. Okay? And if we look, the net force in y is equal to the normal force plus the tension in y, right? Plus Fty. Okay? Because this string is pulling up a little bit, the table doesn't have to push as hard, or the ground, or whatever it is, on the crate or the sled or whatever. And so there's a little bit less normal force, which actually causes a reduced frictional force. Okay? And then minus Fg, because that one's pulling down, has to equal 0. Okay? And so then Fn is equal to, if I add the Fg over and subtract the Fty, this, and so now I can say that the normal force is equal to mg minus Fty, okay, and Fty is the opposite side, so I'm going to be using minus 60 times the sine of 25 degrees, okay, and then you can plug in your normal force here and your cosine, or your kinetic frictional force here, and you can get your coefficient of friction. Okay, so you got to be careful when a rope pulls at an angle because it does affect your normal force. Okay, the other kind of problem I want to look at today is the equilibrium problem. Okay, remember, equilibrium occurs when the net force equals 0. Okay, and so sometimes it'll be like, how many forces are in a rope if this is going on? And it's a little bit weird, but I think the easiest way to think about it is maybe hanging a picture, Okay, I don't know if you guys have ever seen the pictures with the little wires hanging off the side, but you have like, okay, wire here, wire here. Okay, and what are these wires designed to do? Well, they're actually designed to hold the picture up, right? Gravity's trying to pull it down. Here's mg, force due to gravity, which means this actually needs to hold the wire up. This is the tension in the cable back here behind the picture. Now, the question is going to be, is it better to have a long cable here or a short cable here? Well, you got to think about where this tension force is coming from. It's actually in the cable, which means we have components of weight. This side of the cable is going to have some of it. This side of the cable is going to have some of it. And they're also both going to be pulling this way. They're pulling towards each other because of the way that the forces are arranged, right? Because this tension force is this way, and this tension force is this way. Okay, so if this is FT1, okay, and this is FT2, and those are considered to be equal as long as the pin's in the middle, then what you can say is, and this is angle theta, okay, then you can say, okay, FT1 y plus FT2 y, that would be this side and this side, equals Ft, and since Ft is balancing gravity, that's equal to mg. And so then you can find this side of your triangle, and from there, given an angle, you can find the hypotenuse of your triangle. Okay, and there's a couple problems like this that I want you to work in the book. I want you guys to take a look at, let's see, I want you to take a look at page 135 and go through 42, 43, 44. Actually, let's just do all of them on that page, 45 and 46. Okay, those are decent problems. Let me know if you have any questions about them.